Welcome everybody, you're watching Mr. Fugu Data Science. I decided to make another video doing 10 more real data science interview questions I've came across personally. I would like to say thank you to those who started watching my channel, as well as my subscribers. The code will be in the link in the description below. If we're looking at a random forest classifier, which of the following involves randomness? Choosing which trees to discard during inference, which loss function to use, which subset of features to use for any given tree, or which branch to follow at a given node. You say, oh wow, this is intimidating because it seems very likely that any of these could be the case. First of all, I could say I would probably get rid of this second one right here. The first, third, and fourth though, I have to evaluate. So let's kind of do some inspection. What exactly is a random forest classifier? A simple explanation, I could just say that we're putting together multiple decision trees, merging them, averaging, and then getting a more accurate and stable model from there. We are doing classification, but it could be used for regression. It's a predictive, not a descriptive tool, and it's pretty robust from overfitting, unlike a decision tree. But now, if we are looking at this and we say, well, each tree is built from a random feature let us selected, or features. And we have to note that not all of these selected features or even the observations are known to all trees. So this is leading us to one of the answers. Now, this is really good because the random forest is helping us avoid correlation and overfitting, and when we look at these answers, it would appear that this would probably be the best answer in my opinion. The branches which to follow are interesting because the higher the node on the tree, the more important it usually is. And when you're moving down the branches, you're creating many subsets from your data for it to move through. So this I wouldn't necessarily worry about because this is something you don't really have to worry about. It says which involves randomness. While subsetting these trees is working on randomness, and that's what I'm thinking is going on here because that seems the most important. Now let's look at SQL joins and figure out which result would incur more matching rows than either the input tables. So this is interesting, and I had to think about this because it said more matching rows. That's the key point that you have to remember. Remember what the outer, left, right, and inner joins are. If we're looking at the full outer join, we're basically taking everything from the left and right side if everything matches. And then anything that doesn't match is just a row that has null values. The right and the left join are basically same, but they're in reverse. So you're returning everything from the right table and anything that matched in the left. And then anything that's not matched is just a null value. The inner join is, you could think of an intersection of both tables. Okay? So the real question is, what is creating more matching rows? Well, I would have to say the inner join. Okay? So there's a few reasons why I would say this for examples. So give me a second. So here we go. For our joins, the inner, the left, the right, and our full outer. Okay? So now that we come back here and we see this, why did I say more matches? Well, you have more matches for the inner join because you will not have any of these rows that are populated by null values. So while you get from a full outer, left, or right join more rows in total, the null values are what you have to reconsider. So if we're doing a trade-off between speed and accuracy when calculating the product of many probabilities, how can we take care of this? And it says which approaches. So you have a big int, you have a float 32, for example, single precision, you have a Fourier transform, and a log sum exponential trick. So it looks like we're using 2 of the 4, but which ones are we using? To think about this, it's very interesting, and there's a lot going on. So if we had many probabilities we were dealing with, we could assume that we would put them into some form of a matrix. And if we were to do that, the matrix multiplications can be a problem. And you'd have to think about something like this. So your time complexity is horrible. And if we had, for instance, 2 matrices that were 10 to the third, you would now have 10 to the 6 operations, which would be 1,000,000 operations, right? So you're like, oh no, what's going on with this junk? So then you say, alright, There are algorithms that take care of reducing time complexity for matrix multiplications, but you have to do tricks. So that's one of the things for the speed up that we need to consider. But the other thing we need to look at is accuracy. The accuracy, our two options are the big int and the float 32. Now, if you're looking at this problem as a whole, you have three things you need to consider. One, converting your multiplications to additions. When you do that, you automatically get a speed up. Two, underflow and overflow for accuracy of your probabilities is something you need to consider. Underflow meaning that if you had a really small number getting close to zero, like 0.00005, something like this, you could end up with just zero showing up instead, which is a problem. Hardware versus software is something also for speed. For instance, the single precision 32 would be a hardware setup, whereas the big int would be a software implementation. Now, these days, the distinction between hardware versus software implementation for speedups are fairly close together. So if we were to look into these, we would see that the log exponential trick, while it's good for doing multiplications and converting them to additions, you have issues with underflow actually. And then you have the float 32, which is good for adding and slower for multiplications. So if you indeed used the log sum exponential trick with the float 32, you might be pretty good, except for this underflow issue you'd have to figure out. It depends on what kind of operations you're doing. If you're building a bridge and you only needed something to be like within a quarter of an inch or 2 inches, then it doesn't matter. But if you have something that needs to be like 10 to the minus 10, you're going to have some issues. Then the big int is the reverse of that, where it's really good with multiplying but not so good for additions. And then that Fourier trick is really interesting because it's not bad time complexity, it's n log n, and it's really good if you have large amounts of data, if I'm correct. If I were to choose two of these, I'm not sure which two I would choose, to tell you the truth. The big int would not be one I would think about for working with floats, so my option would have to be this. Also, if you're getting into double precision, the larger you get, the slower the computation is. So I would have to consider saying you need the float 32, but between these two, I don't know. Probably the Fourier transform since the underflow issue, but I don't know. Now, if we're comparing a validation set with a test set, can you do this? Well, it's kind of a problem because you got to think about your original data. Like if you have enough data, you can do a train, validate, test where you're splitting your data. Now, you're using the validation set to address any problems you may have in your model and adjust and tune your parameters. Because in essence, what you're doing is trying to avoid overfitting your model. And the test set is something that you're not using on any of your original data to basically see how good your model is. Now, streaming a data set. This is something that I have only had come up once in my life, and streaming data is really interesting and challenging. So, if you are only able to read whatever you're streaming one time because it's too big and it just doesn't fit into memory, can you do a mean, a variance, both, neither, one or the other? And this was something that I just was uncertain with because I haven't had to do this. And doing some research, I found that there's algorithms that are good for one pass. That's what you'll look up, one pass algorithms. And there's things built for this for streaming data. And it appears that something called a well-forward algorithm is good for finding the variance, and there's variations of these algorithms. And then you could apparently do a recursive call to find the mean of your data by taking your current data and then whatever was previous, like just came in. So it appears that you could find both. Now, what are some assumptions when you're looking into naive Bayes algorithm? Well, this does look promising to say, well, you would have a normal distribution as an assumption, but you would not be correct because there's not a distribution assumption. Linearly separable. Now you have two independents, and you need to choose conditionally independent. That would be your answer for this. Now, if we are looking at reversing a list, how do we do this? Well, as soon as I looked at evaluating these, I had to figure out, well, we need to go to the end. We need something that goes to the end. And this -1 looked very promising. But then you say, well, what's going on with this -I? And I remembered from algorithms, and I said, oh yes, I remember when I had to reverse some stuff, and this is actually what I need. Because you need to take what you're looking at, and then you need to subtract it from the end. And if you notice here, that's what's going on, and that's your correct answer. And mind you, if you're looking at these and have 1 minute to think about it, you can't really solve the problem. You just have to know, okay? You have to have some vague idea of what's really going on. So put that into context. So if we're looking at some queries, and we say we have both of these queries, and we need to think about what are the differences. And I put here, think about the distinction between these, because you're having a group by versus over partition by, where both of them you are using an average. And so what's the distinction? The first thing. So what are the answers that we have to work with? The first one computes the average price for the category while the second does not. The first one is not valid SQL code. The second one is. The first returns unique categories. The second may return duplicates, duplicate categories. And the first one is less efficient to compute than the second. You say, well, what's the answer? Let's think about this. A group by is used for doing like sums and averages, but what it does is it collapses and returns less rows, while over partition will return the rows preserved. Okay, and it's a window function. So what does that even mean? Well, if we're looking at these, I'm going to chuck this out because these are valid SQL code. Now, the second one does not. Well, this one looks like valid SQL code too. So it says we have these two. Now you have something with efficiency, and then you have something that's returning unique categories. Well, this efficiency is really interesting. And if you delve deeper into this partition by with this over, you notice that it does a sequence of operations to perform this, where you're first doing a sort and then it's doing some kind of aggregating, and maybe that could be slower than doing this operation. But when I look into the research, I don't really see anything that's definitive that could prove this assumption. Maybe I'm wrong, maybe there is something here, but I don't really know, and I'm going to avoid saying that, and I'm going to keep this one, because this is giving unique categories because you're collapsing these rows. And this one, while it may reassign your row IDs, it may look like you're actually having a duplicate in some rows, but you're not actually duplicating all your values. You know, so you may have like a row ID that may look different, or you may have some information that looks the same, but you're not actually creating more data than you have. Now, this would probably be my answer. If we're looking at what actually is a activation function, like you would use in a neural network, well then what's really going on here? You know, like what is it? So if I was to think about that and give some kind of short answer, I'd have to think this. If we were thinking about what an activation function is, I'd preface with saying think of an on-off switch. And you're doing this with weighted sums and applying it to a bias term. And you need to introduce some kind of non-linearity. Because if you are leaving this as a linear function, just think of running a regression, you know? You're not able to make a model, you're not able to make any complex models, you know? And so basically, the output being received and updated depending on the weights and biases for your error. Now, if you're considering the input where you're looking at the current neuron and moving to the next layer, and the neuron will reach the activation function and it'll be on or off, right? And there's two different kinds, either linear or nonlinear activation function, okay? And you can think about that here where you consider your neuron, you have your input, an activation function can look like, such as like think of a gate, you know, and you're feeding in your input neuron and it's outputting it to the next layer, right? And here's your activation function, here's your weight, and here's the bias that you're adding into it. And basically it's deciding whether this neuron should be activated or not activated, okay? So what's wrong with this code block? So you're doing a try and a finally, and you're trying to open some file and you're trying to read it in, and then you're closing the file. And then you have a few answers and it says not all the bytes from the file are read. The file may be closed before all the data is read. If you fail during opening, a different error code will be raised. If an error is raised, the file will remain open. Well, the third answer right here is the correct one. And this is because any caught errors, this is because you will not have caught any errors. And you can use either a try and accept, or a try except and an optional else clause to kind of take care of any errors that may come up. So we'll scroll down here. So something like this. So an OS error that you can say, or you can call a value error. Here's an example of what you can do. And here's another example right here. So that's what I would say for that. So let's do this last one, which is very involved. There's a lot going on with this. So which of the following expressions defines the variance of a random variable x? If you're doing this, you need to realize a few things. The expected value of x is your mean. So here, this is just the x squared value. It's not the mean squared. All right? So the first one doesn't appear to be what we need. We do need a squared term, such as one of these, but this is definitely not what we need. So you could rule out these two if you solve these. And the third and the fourth one are really interesting, but you have to realize something here. You're now squaring the mean here, then you just have some random variable x. But what's going on is you in turn have two variances of x which cancel out to 0. That's definitely not what you want. So the fourth one right here, like I said, you need something that's squared when you're looking at this is going to work. You got to pay attention to how this notation is. Okay? So it's just like doing your squaring when you're, doing a quadratic or something like that, So this is the breakdown of what it looks like when you do it. But mind you, if you're looking at this and you're doing this for an exam, it's not going to be very fast. So you do have to realize that you need a squared value, but then you have to figure out which squared value you're going to need. Alright? So I'd like to say thank you for watching this video. I hope it brought utility to somebody. Please like, share, and subscribe, and if you subscribe, turn on that notification bell. As always, I'll see you in the next video. Thank you for watching. Bye.